Right, thank you. Thank you so much for being here. I'm going to show some work done by transmission electron microscopy on the most volatile rich sample brought by the Apollo missions to learn about the alteration events that recorded in this sample, which has been debated for decades. Next slide, please. Currently, 3 different types of volatile reservoirs are recognized on the moon. We have the primordial volatiles originating from the moon's interior, the surficial volatiles, and the polar volatiles sequestered in permanently shadowed regions at the lunar poles. These 3 different reservoirs interact with each other, and then they may make up a lunar water cycle. In particular, there are some samples associated with volcanic eruptions that serve to understand the origin and characteristics of interior lunar volatiles and their behavior during transport and eruption into the lunar surface, like pyroclastic gas-driven deposits and samples associated with fumarole deposits. Therefore, these samples are key to constrain the origin and distribution of volatiles in and on the moon, to assess the role of volatiles, and to answer other important lunar science questions like, did the moon ever have an atmosphere, for example? Next slide, please. However, a coherent understanding of the origin and evolution of these deposits, no, the other one, please. We have the origin and evolution of these deposits, pyroclastic gas-driven deposits and fumarole deposits, is still lacking, and the relationship between gases in pyroclastic gas-driven deposits and fumarole deposits is still unclear. In this study, we have investigated a sample of 66095, which is associated with a fumarole deposit. Next slide, please. This sample is a unique impact melt rock. It was brought by the Apollo 16 crew at the from the Kailai Plains, and it's also called Rusty Rock. It's very famous because it's the most volatile rich sample returned by the Apollo missions. In here, you can see an original examination of the sample, which it was quickly brought the attention by this metallic rust on the surface of the sample. This is a breccia, so it consists of a variety of clasts from basaltic to anorthositic, but it has this abundant evidence of alteration. Actually, the volatile rich phases are already also seen within the sample, inside the sample. Next slide, please. The geochemistry of 66095 is consistent with volcanic outgassing models. The sample formed by condensation of a cooling gas from an ancient impact-generated lunar fumarole in the region of the Kailai Plains. So 66095 is an example of a volatile-rich surface rock, and the volatiles are inherited through vapor condensation from an internal volatile-poor lunar source formed during the thermomagmatic evolution of the moon. Next slide, please. So although the sample has been examined over several decades, especially for isotopic systems, a detailed examination of the alteration assemblage on the I'm hearing myself, sorry. The alteration mineral assemblage on the nanoscale is still limited. So the goals are to constrain the source of volatiles in Rusty Rock, to get insights into these lunar interior volatiles and their behavior during volcanic eruptions and lunar surface processes, assess the formation mechanism of the rust. That's why that's one of the main goals, and then look for potential of these volatile rich lunar samples to understand what's going on with these volatile rich samples when they are going to be brought back to Earth. How are we going to preserve these volatiles by on Earth by the Artemis missions? Next slide, please. You can put them all together. This is the sample that we have investigated. It's a 2 millimeter size sample of 66095, which was kept in nitrogen atmosphere, in pristine nitrogen atmosphere since its return from the moon. And it was prepared at NASA Johnson Space Center, where they place it inside a borosilicate glass container in pristine nitrogen atmosphere, and they send it to Barcelona, where we perform micro XRD analysis in synchrotron light. And then we open the sample and we let it interact for a couple months, and we repeated the analysis in the synchrotron. So once the sample was already open, we place it in epoxy and we prepare 3 FIB sections that we studied by TEM. Next slide, please. This is an image, an X-ray RGB SEM image where iron is in red, magnesium is in green, and silicon is in blue. And you can see that the metal grains are easily seen by these red faces. These 2 squares in yellow are the 2 regions that I'm going to zoom up in the next slide. Next slide, please. And in here, you can see, you can put them all if you want. The first, you can click all of it. This is the first metal grain with this associated material, because we know that the rust is associated with metal grains. And then in this other region, we got 2 more FIB sections. Next slide, please. That's the first FIB section. You can see the metal grain on your right, and then you can also put all the clicks in this slide. Okay, that's it. It's associated with a relatively large Stanfieldite grain, which is a very rare calcium magnesium phosphate found in stony iron meteorites. So at first, you can think that this Stanfieldite is coming from an impactor. It shows complexity. It has basically from shock, but it also has nano-inclusions and nanoporosity. And then I'm going to zoom up another region. Next slide, please, in here. On your right bottom, you can click, please. And next slide. And it's this region where iron nickel metal is associated with acagenite, which is the rust. Is this chloride containing iron nickel oxyhydroxide, which is amorphous in this case, and we have a nickel and chlorine richer region closer to a chromite grain that has a lunar composition. And we have also something going on within the Stanfieldite and chromite that needs further investigation, because it can give additional insights into this alteration event. Next slide, please. That's the second FIB section, where I just, it mainly consists of anorthite and pigeonite, typical of this type of lunar sample. We have the metal grain, and I'm just going to highlight some of the main features. We have this mobilization of magnesium around the sample, where we have magnesium poor regions and magnesium-rich regions, and some magnesium concentrated in bands around the sample. I'm going to highlight 2 more regions in here. Next slide, please. That's the first one, where you can see that we have this magnesium concentrated in bands. Then we have altered phenocrysts like armalcolite, and another calcium magnesium phosphate that's closer to merylite composition but has more magnesium content. We also have some silicon and some zirconia. Next slide, please. And then we have this vein, which is large, and it mainly consists of acagenite. You can click 4 times, I think. The vein basically consists of acagenite. We also have iron nickel and some regions where we have chlorine concentrated up to 15 weight%. And then we have also these nickel-rich veins within the larger vein. And again, in the matrix, you can see the magnesium concentrated in bands, if you click, which is in yellow. And next slide, please, the last FIB section. It's this one. You can click. Yeah, that's it. We have the third metal grain, which is associated with ilmenite, which is a lunar phase. But in here, you can see another metal grain, which has slightly different composition than the larger one, which is being altered to Stanfieldite. It has a different morphology in here, more like a vein, and it's altering ilmenite, which is a lunar phase. So in here, we can see that the Stanfieldite was produced on the moon by alteration of metal. So next slide, please. In here, in this sample, we have many different phases from lunar origin: anorthite, pigeonite, ilmenite, chromite, armalcolite, and zirconia. Then we have this Stanfieldite, this very rare calcium magnesium phosphate that's found in stony iron meteorites, but We also have this other, well, and also this merlylite with more magnesium content. But we can see, especially from fifth section number 3, that is coming from alteration of iron nickel metal grain on the moon. So the alteration was produced on the moon. This mineral phase was produced on the moon. It does not come from an impactor. The iron nickel metal grain could come from an impactor or not. This is not clear, but what is clear is that Stanfieldite occurred on the moon. And then we also have this akaganite that we think it's from a terrestrial origin, a low temperature alteration of lawrencite by oxidation of anhydration. However, we didn't find any lawrencite in our fifth section, so we still cannot rule out a lunar origin if, for example, the gas from the lunar fumarole changed from chlorine dominant to OH dominant. But the most likely mechanism of formation is terrestrial so far. Next slide, please, and last one. So basically, we have an impact-induced fumarole activity on the moon that mobilizes magnesium around the area and other elements. We have alteration of iron nickel metal that releases phosphorus, and together it forms Stanfieldite on the moon. We need more data for Stanfieldite. There's very little experimental data and phase diagrams from this mineral that can give additional insights into this alteration event that was produced on the moon. And finally, we think that the rust is a terrestrial alteration product, but we still cannot rule out a lunar origin. So we need more work, more TEM work on another sample that will never be exposed to the Earth's atmosphere when we will perform this type of TEM analysis. Thank you very much. Sorry for the technical problems, and I'm happy to take any questions.